Many people think that the internet is just there and that it always just works. In reality, an enormous amount of infrastructure exists behind the scenes to make the internet just work. In this video, we will use the computer network at the University of South Florida to show you what the internet infrastructure of a modern enterprise looks like and what it takes to keep it running. The network is the foundation on which all USF communications are based. Whether you're using a desktop PC wired to the campus network or a wireless mobile device such as a laptop, tablet, or phone, the network transports your traffic to servers throughout the campus and around the world. You will see USF's network from the desktop all the way to the campus core. We will show you the cabling, switches, routers, and wireless access points that enable high-speed connectivity throughout the university. To help guide you during this tour, we'll first take a look at a high-level network diagram. Because USF's network is made up of nearly 10,000 pieces of equipment, providing connectivity to over 70,000 switchboards and 4,000 wireless access points, it's impossible to include every element in a single graphic. At the top of this diagram, you can see the Tampa campus core. It is made up of two redundant devices which provide 100 gigabit per second and 10 gigabit per second connectivity to the distribution layer devices shown in the middle section. Those distribution layer devices then provide 10 gigabit per second and 1 gigabit per second connectivity to surrounding buildings shown in the bottom section. Within those buildings, there are aggregation devices which provide connectivity to wiring closets. And within those wiring closets, there are devices which connect the individual desktops and wireless access points. Since USF's network is very large and complex, our tour will focus on the connectivity to one specific desktop. This desktop is located in the computing lab in the ISA building. This diagram shows a simplified view of the network. The same core, distribution, and access layers are shown, but we are just looking at the network devices which connect that one PC. We'll start our tour at the access layer or edge of the network. It is here that desktops, both wired and wireless, connect. Most desktops at USF are connected over Category 5E or Category 6 copper cabling. You can see that this desktop has a patch cord running from its Ethernet network interface card to a nearby wall jack. The cabling for this wall jack runs through the ceiling back to a wiring closet. We call this room an Intermediate Distribution Frame, or IDF. This room serves as an aggregation point for all of the copper cabling from desktops in the surrounding area. IDFs can serve desktops on the same or different floors. Most versions of Ethernet are limited to distances of 100 meters over copper cabling. So it's important to position these IDFs so that the maximum cabling distance isn't exceeded. We will now look at the IDF servicing our example desktop. This room houses Ethernet switches that connect to all of the copper cabling from the various desktops and access points in the area. The cabling is terminated onto patch panels in a rack, and patch cords are used to connect those jacks to the switches also located in the rack. Terminating the cabling on patch panels allows for easy replacement of network equipment as new technologies become available. If we ran the cabling directly to the equipment, not only would cable management be difficult, but the cabling might not reach as new equipment was installed. Each stack of switches is redundantly uplinked to separate building aggregation switches. Looking at our simplified network diagram, you can see that the top and bottom switches in this stack have fiber optic connections going to different building aggregation switches. Typically, we design the primary uplink to run at 10 gigabit per second and the secondary link to run at 1 gigabits per second. This helps reduce cost while still maintaining redundancy. The fiber connections from these switches run to fiber patch panels very similar to the ones you've seen for copper cabling. This fiber runs from the IDF to the Building Distribution Frame, or BDF. The BDF serves as an aggregation point for all of the building fiber, and it houses the network equipment which connects all of that fiber. Before leaving this IDF, we should discuss some environmental requirements of the room. Network equipment generates a certain amount of heat, so it's important when designing a wiring closet that we make sure sufficient air conditioning will be provided. We must also be able to continue running the network for at least some period of time during a power outage. This means that we must install uninterruptible power supplies, UPSs, to provide power to our IDF equipment. In buildings utilizing voice over IP for telephony, we are required by university policy to run the network for at least 90 minutes during a power failure. This allows phones to continue operating for emergency calls. Many of our buildings have backup generators that will automatically start after power has failed. But we still need UPSs to get us through the brief outage while these generators start. Now we will look at the BDF upstream from the IDF we just visited. The fiber optic cabling you saw in the IDF runs through the ceiling and often through conduit to the BDF. When it arrives in the BDF, it is terminated on patch panels just like you saw previously. From here, fiber patch cords connect to the building aggregation switches. As you can see, there are two aggregation switches in this BDF. One provides 10 gigabit per second connectivity, and the other provides 1 gigabit per second connectivity to the downstream IDFs. The speed of the ports are determined by the installed optical modules. These optics commonly used today are called SFPs, small form factor pluggables. As you can see in our simplified network diagram, we have moved from the desktop to the desktop aggregation to the building aggregation point, but we're still in the access layer. From here, our building aggregation switches uplink via fiber to the equipment in our distribution layer. These fiber optic connections leave the building and run underground to what USF calls a distribution node. These nodes serve as aggregation points for fiber to surrounding buildings. As of 2013, USF has 6 distribution nodes to meet the computer networking needs of its entire campus of approximately 1 square mile. The fiber patch cords you've seen so far have been orange or aqua in color. This typically signifies multi-mode fiber. However, if you look at the building aggregation switches in our BDF, you'll also see a yellow cable connecting to each. This is the single-mode uplink leaving the building. The jacket you see around fiber is there to protect it from day-to-day handling. Fiber optic cabling is basically just a very thin piece of glass through which light is sent. This glass must be carefully protected. If you strip back the jacket of these fibers, you will see a smaller cable inside. And if you remove the plastic that covers this smaller cable, you'll see the tiny strand of glass that is the fiber optic cable. That strand of glass is capable of sending hundreds of gigabits per second of information over tens of kilometers, but it is also extremely fragile.